Hello everyone. This is Rashid Kibria from FX Research, University of Florida. In this short talk, I will try to explain why FSMx-Ultra is much more better than FSMx. In our paper, you will find all the details there, why it is extremely fast compared to its previous version FSMx that I have already presented at IEEE VTS 22 conference. But if I make a summary there are a couple of regions. The first region is that FSMx analyzes the entire net list once. That means the entire net list, which is a collection of a large number of nodes and edges. That means the V's and E's of a certain graph. If you try to analyze that, inherently it is much more complex because the graph size that is being considered is extremely huge, and you have to perform a lot of computations there. Whatever graph algorithm you use there, that is one of the reason. The next thing is that FSMX performs exhaustive uh, gate level simulation. That means the exhaustive simulation based on generated test benches, which checks for each and every condition to identify the hidden don't care states and transitions. These two regions are the main thing for why FSMX is less scalable to large scale designs. For example, OpenRISC um, to 1200 core, which has around 500,000 plus NAND gate equivalent gates. It is really extremely complex. So you cannot analyze that with FSMX, but it is possible using FSMx-Ultra. That you can clearly see in this table what is presented here. So these two regions are makes FSMx-Ultra unique compared to FSMX. And if you look here, the speed up, the relative speed up of this picture, the table picture that is already taken from our paper. So if you look here, the speed up is really very high, especially for the large and complex benchmarks. And in many cases, FSMX failed to analyze the netlist because the state transition logic had too many number of primary inputs. As you already know that if your number of inputs n increases, then the total number of patterns that you can apply, it also increases exponentially. That means with 2 to the power n. So if you try to perform exhaustive gate level simulation of the extracted state transition logic, your method will obviously fail because of this scalability issues. I have uh, overcome this problem using ATPG based analysis technique. So which is a very fast and industry standard technique, which also tells you the regions for the state transitions, is also able to identify the hidden don't-care states and transitions that I have already shown in my paper. So that is the main point here, basically. So if you look here at the benchmarks, these benchmarks are taken from several open source repositories. They also vary in terms of application, complexity, and size, and also their complexity of the graph. So in this row, that get count basically means it not only includes the simple basic combinational gates, but also the complex ones. That means like AOI22 gate or OI22 gate. That means the other complex logic gates that you may have in your standard cell technology library. FSMX and FSMx-Ultra both can handle any sort of technology library. So our technology is something like that. It can. We have also tried analyzing the technology library from various vendors, including Synopsys, Cadence, Global Foundries, and FSMX and FSMx-Ultra both can handle any sort of technology library. We have also worked with 14 nanometer technology or something like that. Yeah, all of those were analyzable, no issues. And this gate count and a flip-flop count, that is basically all the sequential cell count that you may have in a certain design. And all of these reports you can obtain from design compiler or cadence genus. The edge count, this is the number of edges that certain graph may have. So if I interpret here, these gate counts are basically the node count of a certain netlist graph, and the edge counts are all the number of edges that may be present in a netlist graph. That is the thing. And if you look here, the edge count also varies significantly. It is because of the complexity of the designs, their interconnections, and based on that. So the netlist you get after logic synthesis. The number of strongly connected component count is shown here. So there is an algorithm called Tarjan's strongly connected component algorithm or SCC algorithm that you can use to identify all the SCC regions that is present in a certain graph. You can also apply it to netlist graph, no issues. So that will provide you the number of strongly connected components in a certain netlist graph, and this result is presented here. And the total number of FSMs that is present in all of the benchmarks that is shown here. You can get this information using any tool like RTL FSMx or design compiler or cadences, Jasper Gold, whatever you want. Any RTL level analysis tool will work. Now that basically provides you the number of FSMs that is present in the RTL description. But these industry tools are basically for the RTL level. You can use that information because obviously you will have that much of FSMs there. But one thing I want to point out that if you have a single FSM, but say it is instantiated two times. That means you have two instances. One is U1 and U2, but both of them have the same FSM. In that case, FSMx-Ultra will provide you both the two FSMs, because these two FSMs, after logic synthesis, you will have these two FSMs in the netlist. That's why it will be extracted by FSMx-Ultra. That is the reason. But in RTL abstraction, you will have a single FSM, but you can somewhat match them, right? So that is the thing uh, I want to point out. That is the interesting thing about FSMx-Ultra, is that it can extract all the control FSMs. Does not matter how much an FSM is being instantiated, it is able to extract all of them. And also it reports you all the registers and registers. The FSM, if you look here, there is a discrepancy between the SCC count and FSM count. The reason is that the strongly connected components are the regions of a graph that has at least a single loop. So the FSMs are the regions which has a self feedback loop, and they also try to influence others. So of course, if you try to analyze strongly connected components, just if you look into the SCC regions instead of looking into the internet list, uh, that significantly reduces the computational complexity. It was the main motivation behind FSMx-Ultra, that we did not try to analyze the entire netlist at once. Rather, we deconstructed the netlist into smaller parts using Tarjan's SCC algorithm. Then we found the subgraphs, and just to analyze those subgraphs, this significantly improved our runtime. That you can also see here in the presented table. And another reason is the issue that I have already mentioned, the ATPG-based technique versus exhaustive simulation. These two are the main factors. So why FSMx-Ultra is the next generation of FSMx. There is as I was talking about, there is a discrepancy between the SCC count and FSM count. They are not identical, because SCC count, this can include the accumulator register, the accumulator type registers, or counters, or whatever the other non-straight registers that may have FSM like properties. So Now, rarely it matches the SCC count with the FSM count. It is also appeared from this table that only two cases we have the FSM count, which equals to the strongly connected component count. Now, because there was a single FSM and no accumulator or no other counters were in the design, that's why you did not have any other SCCs. But if you look here, for say for SHA 512, it has um, 1005, 1005, this number of SCC regions, but we have just a single FSM. So it is extremely difficult to find this FSM from this region. That is what FSMx-Ultra has already done. And here I have presented the flip-flops, the number of flip-flops that is present in the FSM register. So if you look here, it also varies. Like it has also a small number, like 2, 3, 4, and it also has a very large number. For example, 66. Like for this benchmark, that is the memory controller, the number, the FSM flip-flop is extremely huge. It is because this core is encoded using one hot scheme. That's why it has total 66 states, and all of them were encoded using one hot encoding technique. That's why we have total 66 state flip-flops. But for the other steps, they were utilizing the simple binary encoding. That's why you see a very small number of FSM flip-flops. And here I have presented the FSM input similarity metric in percentage. You can find details in our paper. And this is the FSMx runtime and FSMx-Ultra runtime, and finally the speed up. So if you look here in many of the cases where FSMx actually took around minutes, but with using FSMx-Ultra, you can just analyze them within seconds, just within a minute, right? So say for this AES 120 design that is from SecWorks, it took around 6 minutes, around 6.5 minutes using FSMx. But with FSMx-Ultra, you can analyze the same design, get all the FSMs from there within only 31 seconds. So it's significantly this is faster, and also FSMx-Ultra is it is really so much scalable. The reason is that it can analyze this open risk core, which has around 500,000 plus number of ASIC equivalent gates. So if you look here, it was not analyzable using FSMx, but FSMx-Ultra analyzed that within 7 hours, and it extracted all the 5 control FSMs from there. That is the thing why FSMx-Ultra is so much better in terms of performance compared to FSMx. Thanks for hearing.